Okay, let's start, I guess. So, to recap where we stopped last time, we came up with the this one sharp formulation of the question what QCD strings are. Namely, we decided to take strict planar limit and consider infinitely long string, which in this limit, and now I'm finally getting to QCD strings, so I will talk about SUN C Young-Mills theory, and actually I will be simultaneously talking about both D equals 3 and D equals 4 case today, in 3 and 4 dimensions. And so, sharp but still interesting, I think, a version of the question of what QCD string is to take infinitely long string, consider strict planar limit. In this limit, Wolff-Sheet theory decouples from all the rest, and one can study S matrix for scattering perturbations of the string, and this is a in this limit, this is not effective theory anymore. This is a UV complete theory. The scattering keep being unitary up to arbitrary high energies. And there were also we learned that well, there is a piece of bad news here, which also it depends on how you see it. The piece of bad news is that unlike in critical string, when you do the same in critical string, then Wolff-Sheet theory becomes integrable. Here, well, at least at D equal 4, there is inevitable particle production, so the theory is not integrable. At D equal 3, so far we saw that there is a room for integrability, but we'll see later today that just lattice data shows that also in D equal 3, theory is non-integrable. So that means we'll never solve Young-Mills in the planar limit. And so, well, the question is what we can do, and we should somehow ask for some different questions. And well, I can see two questions one can ask. First one can ask, is there a confining theory which is integrable in this sense? So usually when we discuss integrability, we talk about two-dimensional theories, but here we start from high-dimensional theory and reduced the question to 2 dimensions. And so we have an example of conformal theories, which are integrable in this case, famously unequal force superior Mills. So it gives rise to hope that maybe there are also confining theories that are integrable in this sense, or if not, it would be interesting to prove kind of some no-go. But another question one may try to ask is, well, whether, well, we saw that low energy dynamics is approximately integrable just as a consequence of approximate integrability of Nambu-Goto theory. But one may hope that, so at high energies, the theory which we started with is free. So we started with asymptotically free theory. And so, but then we took high energy limit in somewhat non-trivial way. There is non-trivial order of limits that we took first and C into infinity limit and then high energy limit. But still, kind of that gives rise to a hope that maybe there is some memory of at least freedom of the bulk theory, which still remains in even on the Wolff-Sheet, and so maybe it's possible to develop some high energy perturbative expansion perturbation theory. Similar how we always do that in QCD, but here the complication is that we want to deal this sector and with this non-trivial order of limits. So I think that's at least 2 possible directions which I can see how one make progress. But well, as I said, so that sounds like a piece of bad news that the theory is not integrable. But you can look at this differently. the fact that we taken this order of limits by obtaining UV complete theory, well, it tells us that, well, actually, and I think that's for me at least, that's the reason why this whole story is so interesting, that what we're dealing now in this limit, it's really a theory of two-dimensional gravity, right? So because it's a theory of dynamical two-dimensional surface, and the fact that kind of it cannot be broken, that there's no pinching off, that really tells us that kind of it's a microscopic theory of gravity. And well, we already said, so when one does the same exercise in string theory, when one looks at the string theory in the limit Gs equal to 0.
But in gravity you do expect, like value universes, you do expect pinching off. With gravity is supposed to some of the topologies connected or disconnected.
Well, that's kind of, yeah, so this is a limit when topology changes are turned off, exactly, right.
Planar gravity.
Yeah, it's a planar gravity, but still, well, it is, yeah, well, here by the same gravity, I've just been really dynamics of fluctuating surface, but also, well, it's a matter of terminology, but it's not quantum field theory. What we're getting here, and that's one already sees it in string theory case, in critical string theory case. So where there, as we discussed, in the limit when one sets Gs equal to 0, which kind of turns off what we usually call gravity in string theory. But one gets 1 plus 1 dimensional theory, which is integrable, and with this S matrix, as we said. So it's a very simple theory. But this, as seen as two-dimensional theory, well, first of all, clearly it's a theory of gravity, because in Polakov description, it is a theory of gravity. There is integral over metric. But also, just from the form of this S matrix, as we said, well, it has this asymptotics at high energy. There is time delay which grows indefinitely with energy, so there is no UV fixed point. So it's not kind of, if you wish, what I call here by gravity, it's not a local quantum field theory in 2 dimensions. What one gets there, and then we can discuss whether it's proper to call it zero gravity or not. It's kind of somewhere in between, because but the fact that this theory is not integrable tells us, well, that actually in QCD case, that theory is even closer to actual theory of gravity. There is particle production there, and so kind of as a piece of good news, we can do experiments in that theory, and by experiments I mean mostly lattice data, but actually not necessarily, and so there are not that many examples where we can do experiments in gravitational theory. So from that point of view, it is a piece of good news. And also, well, by now we learned that gauge theories and gravitational theories, they are not, well, they're closely connected, and that may be one of the kind of most basic examples of this connection. Okay, so so in this spirit, what I will do now, I will summarize for you what actually we know by now experimentally about this series. Well, having in mind these 2 questions which I just erased here. And so the experiment, that's lattice simulations, and what one does in the lattice, already discussed it briefly, but so one takes theory on a cylinder. Well, of course, on the lattice one considers Euclidean theory on a 4-dimensional torus, but for the purpose of what I'm going to discuss now, it's useful to think about it as really a theory on a, think about one of dimensions is really physically compact, and it's Euclidean theory, but for it's useful to think about this as a spatial direction. And then what one does, one studies 2-point functions of the Polakov loops, or Wilson loops, which wrap around this compact dimension. Well, these don't have to be straight Polakov loops. They have deformations, and then from studying of the behavior, exponential fall off of these correlators, one extracts the finite volume spectrum of the Wolfschild theory as a function of radius r. So on lattice, one cannot directly do scattering experiments, but I said, as usual, one has Euclidean data, which is a finite volume spectrum of the voltage theory obtained this way. And so so to interpret this spectrum, now we need to kind of, now from theory side, we want to have some calculation for the spectrum to compare to something. And that's using what we discussed so far. It's natural to start with a limit when R is large in the string units. So when one can do low energy effective field theory, and here there was actually for a number of years there was a bit of a mystery here, a bit of a puzzle, which was the following. So first of all, kind of what one does, what is the theory calculation one does. One starts with this effective field theory which we're discussing so far, which Nambu-Goto theory plus principal infinite series of high dimensional corrections. One puts this theory on a large circle, and one needs now to compare to data. One needs to calculate the finite volume energies, or energies of finite volume states, as a function of a circle size. And a most straightforward way of doing it would be to decompose everything in KK modes. So one gets kind of quantum mechanics of infinite number of KK modes, and do perturbative calculation in the small parameter, which is LS over R. And actually, from what we discussed, one knows that in this expansion there are lots of terms, lots of like low terms in this expansion. They will be universal. They will be independent of the microscopic theory, because remember this. So schematically, this action starts from this minus 1 over Ls squared, which is just this cosmological constant term. Then there is dx squared, dx to the 4 Ls squared, etc. So there is infinite series of operators coming from Nambu-Goto term. Then the first non-universal correction is associated with operators which appear. So these high-dimensional operators which appear here, they have more derivative per x than the terms which come in from Nambu-Goto term. But given that at the one loop order there is no non-trivial counter term, as we discussed, the first non-trivial correction appears at the order d squared x, d squared x, d squared x, d squared x. So it's coming from something like r squared operator here, which stands here by a dimensional ground. So there is Ls to the 6th, which appears here. So that means if one looks at the expression for energies of the states in this 1 over expansion, well, they all have contribution which starts with 1 over Ls squared over r. Well, and then there is expansion in powers 1 over r. And the first non-universal term in this expansion appears only at the order, well, it should be proportional to this Ls to the 6th, to this parameter alpha. So it appears at order 1 over r to the 7th. So, for instance, well, this is the classical energy, then there is kind of one loop correction. So if one talks about ground state, which goes like 1 over r, which is just Casimir energy, which was called Lusher term. But actually the number of universal terms in this expansion is much larger. Well, which again, depending on how you look at this, it may sound like a good news or a bad news. It's a good news in the sense that this low energy theory is very predictive. But if you want to extract from this data information about high energy theory, actually this universality is not a welcome feature. You need to go to very high orders in the 1 over expansion. Now the puzzle was the following. The puzzle was that, well, there is this universality, so one can calculate in principle all universal terms up to 1 over r to the 5th here. And then one can start comparing them with the data. And for ground state energies, this comparison works very, very well. So this perturbative expansion describes the ground state of a string very nicely. However, for excited strings, for excited states, the comparison was not so good. Well, by itself, it's not a puzzle. Well, it's kind of, it was breaking down just at R, at value of R, much where for ground state the expansion was still very well convergent. But the puzzle was the following. So in the regime where for excited states this perturbation theory wasn't working very well, on the other hand, it was observed the following. So let's take the following spectrum. Let's take the spectrum, which I call LC, for the region which will become clear momentarily, and which is given by this. So what's written here is the following. So if I plug here d equal 26, that would be the spectrum of bosonic string in the sector with winding number 1. And this instead this spectrum.
Are you missing the 6? Or?
No, there is. Oh, what well?
No, it says that d minus 2. Oh.
No,
So it's okay.
Yeah, right. It's correct. Yeah. So in the if I plug d equal 26, then that becomes the bosonic critical spectrum of critical bosonic string in sector with winding number 1. For non-critical d, the way the spectrum can be obtained is that essentially, well, you do analog of light cone quantization in the sector with winding, and close your eyes on the fact that light cone quantization doesn't work in non-critical dimension, and you get the spectrum. So we know that's the wrong spectrum. And the observation was that actually for most excited states, not for all, as we'll see soon, but for most of excited states, this spectrum, the square root formula, was describing the lattice data very, very well, much better than the honest perturbative calculation, expansion in 1 over.
So how was this obtained?
It's obtained by essentially doing light cone quantization and of the Nambu-Godd, right? Yes, that's one way to obtain the spectrum, right?
And it's doing a better job.
Yeah, it does much better job for most states, and actually it does surprisingly well job. So basically, for many states, it works down to, like for ground state, the perturbative expansion was working down to R over LS, really for the 1, maybe 1.5, 1.2, but the same here. For excited states, it also was working very well.
I mean, it's a very simple, mathematically, it is just like the spectrum of a free fundamental string, that instead of imposing L0 equal to 1, you impose L0 equal to d minus 2 over 24.
Wow.
If in the equation for the on-shell condition, perturbative string theory, instead of L0 equal to 1, I will impose L0 equal to d minus 2 over 24, and we get this spectrum.
Yeah, but we know that cannot be correct, right? Because that's
sure.
So, and that's what's the puzzle. How comes there is a correct calculation which works for one state and doesn't really work well for other states, and there is wrong calculation which works almost for all states.
Can you explain again what is the system?
So, one side, well, it's either d equals 3 or d equals 4 Young-Mills theory, and one calculates 2-point functions of this kind of 2-point functions where O's are Wilson lines which are wrapped around closed circle, but possibly deformed in the transverse direction. Or in other words, one studies the operators of this sector of operators A with this set of insertions, and in large N limit, this single trace subsector decouples from all the rest. So one studies this subsector of these operators, and then one approximates this set of 2-point functions as a sum over e2 minus int, sum of the exponents, and from these exponents one extracts the energies. And these energies are interpreted as excitation energies of a string which is wrapped around the complex circle.
So Sergei, this term that you wrote there upstairs, the one that the number of x's and that derivative does not match, cannot come from the number of x.
Yeah, you mean this term?
Yes.
Yeah, this is the first non-universal term. This is term coming from integral to sigma square root of minus g r squared of k to the 4. So that's the first non-trivial non-universal term which can be written in this action. Okay, so what's going on here? Well, actually, to understand what's going on, it's instructive to look already at this formula, and one can look at this formula even in the well, we can think about critical string, but well, there it will be a bit more confusing. But yeah, but basically, what happens is the following. So there is this formula, and vacuum state corresponds to taking this n tilde is equal to 0. So well, there is a square root formula, and 1 over expansion corresponds just to taking this formula and expanding it in LS over R. So there is a finite radius of convergence for this expansion, and this radius of convergence is set by the place where there is a 0 for under the square root. And the 0 set for ground state is the position of the 0 is determined by the value of this coefficient. However, for excited states, the 0 gets shifted because these are integer numbers, and so the radius of convergence gets much worse. But we know, like physically, what these parameters telling us. So this presence of n's, it's telling us that the difference between ground states and excited states, that really for kind of the energies of the excited states, they can be thought of as their so they depend kind of on R in two different ways. So they depend on R. Well, this ground state, that's essentially that's a quantum effect. That's this term is associated with winding corrections, with virtual particles going around the loop. But in addition, there is for excited states, there is the energy depends on the momenta of the corresponding excitations, and of course momenta, they're also quantized in units 1 over R. So when one plugs that momenta in terms of n's, then that's one gets that everything depends on LS over R. But physically, to start with, these energies were physically kind of this 1 over R dependence was coming from two different places, and kind of this naive LS over R expansion, it mixes together these two different places. And so what one may want to do, one may want to organize expansion in different way. So roughly speaking, start from the approximation that one talks about large momenta, so disentangle these two different sources, and reorganize perturbative expansion. And so actually what I'm telling you is, so it's a bit ironic, because like this technique of doing this LS over R expansion, that goes back to work by Lusher, like in 1981, who he was the first universal correction here called Lusher term. So he started this, and then at the same time there are in lattice literature there are Lusher formulas, which are exactly they are designed to solve exactly this kind of problems, because typical lattice simulation, what it does, it calculates finite volume spectrum, say of pions, and one wants to relate that to scattering phase shifts for pions. And and the way Lusher formulas work is that to extract the phase shift, so for free particles you have quantization condition like this. But in the presence of phase shift, scattering phase shift, you modify this, instead of doing this perturbation theory I was referring to, putting zero in a circle and expanding like this quantum mechanics perturbatively and quantum mechanics KK modes, but imposes this modified periodic condition, and the naive perturbation theory based on based on the expansion in 1 over R, that would correspond to perturbatively solving this equation in the phase shift. Which, not surprisingly, that's not a very good idea, especially when phase shift is a rapidly growing function of p. So basically, the proper way to organize calculation is first to calculate perturbatively in Low-energy theory, to calculate phase shift is a function of p. That step can be done perturbatively, but then in principle, one wants to calculate S matrix perturbatively, but then there is second step, which is relation between S matrix and the finite volume spectrum. And that step, in principle, one would like to do non-perturbatively. In particular, what this captures is when you have particle which kind of goes around the circle, that it exhibits multiple, like it interacts with itself many times. And expanding this equation perturbatively, you kind of account only for one instant of this interaction, and so that's not a very good idea. Now, unfortunately, kind of this in general, this question how to, I think we all believe that S matrix has all information in it, but this question of how to relate the infinite volume S matrix to the finite volume spectrum for general theory, well, we don't know the answer yet, although there is some progress being done. But what helps is the following. In this particular case, what helps is that this S matrix, which one starts calculating in Nambu-Gote theory at low orders in LS expansion, or in the momentum expansion, that at first at low orders this S matrix is integrable. That's related to that approximate integrability which we discussed in previous lectures. And for integrable theories, we know how to connect S matrix to finite volume spectrum, namely this equation, which is written here in lattice literature, well, in high dimensions, it's called Lusher equation. In the context of integrable models, that's called asymptotic beta ansatz. Well, and also, in principle, there are corrections, if one wants to account, corrections associated to windings, which are responsible for this kind of term. Then one needs to write thermodynamic beta ansatz. And then what happens is the following. So if one follows this procedure, namely one starts from Nambu-Gote and starts calculating S matrix perturbatively, and leading order in the less expansion is just the phase shift which I wrote for you before, e to the S. Then when one applies to that phase shift, when applies thermodynamic beta ansatz, one gets exactly this spectrum. So this double, like this, doing this finite volume calculation in two steps, separating the step of calculating S matrix, doing that perturbatively, and then going non-perturbatively to finite volume spectrum. In this way of doing things, that formula comes as a zeroth order approximation for what one expects to get. So that kind of largely eliminates the mystery of what's going on. And
where do you get n tilde from? So you have n, which is one quantum number in the asymptotic beta equation. Where does the n tilde come?
no, these are n and tilde. That's the number of left and right movers. So here, yeah, no, this n is different. Yeah, so well, here for two particles, like n is equal to n tilde is equal to 1, and I think what appears here. Well, there is a proper generalization of these equations which one can write
So this one should write equation with n plus n tilde rapidities? Or something like that?
The way it's done in so one should write equation. Yes, there is, in general there is some bunch of n is actually is equal to its sum over kind of ki and I, where k is the level of the momentum of individual particles and n is the number of corresponding excitations, and there is it's the same for n tilde. So it's the level of asymptotic beta ansatz. Yeah, one starts with configuration where one has a bunch of these particles, and one writes for each of the particles one writes periodicity equation modified with one sums over phase shifts, which it requires from all others. For thermodynamic beta ansatz story, it's a little bit more complicated, but one can work out at the leading order here. One can work out exactly equations for thermodynamic beta ansatz, which determine all the spectrum of all excited states in this area. And, one gets this expression. So the kind of the bottom line that there is no mystery here. After one reorganizes calculation in this way, one first understands what's going on, and one can also systematically improve on this. Well, up to a point. At some point in LS over expansion, theory ceases being integrable, and that's kind of in other words, two particle states start to mix with four particle states, and that's where kind of these equations they break down. So kind of one needs to think more seriously about this problem: how to connect finite volume S matrix to scattering to finite volume spectrum in non-integrable theory. But actually, in the context of Nambugota, before that happens, something more fortunately something interesting happens before that. Namely, I remember we were discussing that at one loop, there is particle production which appears, but that particle production that actually appears because it's associated with process like 2 to 4. It's associated with it has a high order in powers of LS. But already at the level of 2-2 scattering, something new happens. Namely, at the tree level, it was diagonal, but at the one loop order, there is this Polchinski-Strominger term, which introduces inelasticity. So if we truncate the S matrix calculation to the order where we include this 2-2 non-diagonal terms, but still drop higher order in LS terms, which introduce particle production, then the result in S matrix it's still integrable in a sense it doesn't exhibit particle production, it doesn't change the number of particles, but it does something interesting. Namely, if we look, now I'm talking about D equal 4 Young Mills, where Polchinski-Strominger is non-trivial. So at the level of two particle states, well, there are four different states where these labels ij can be take values like 1 or 2 in transverse directions, and they can be classified according to O2 rotation symmetry around the string. And so one gets here, one gets scalar, one gets pseudo-scalar state, and one gets two polarizations of spin 2 states with respect to this O2. And so what happens then is the following. So at the leading order, three level Nambugota, because there is universal phase shift, scattering is diagonal, then all these states are degenerate. But this universal one loop effect at the 2-2 scattering, it leads to it predicts now splittings between these two states, and well, actually it predicts that the scalar and pseudo-scalar, the structure of Polchinski-Strominger term is such that it predicts that scalar and pseudoscalar, they remain degenerate, and spin 2 splits for them. And so now one can compare that to what happens in the lattice data. So I'm supposed to show slides, so I will try to draw a plot here. So typical lattice plot, what it does, it produces like energy of the states is a function of R. And when I draw in energy, I will be drawing actually excess energy. So I will always be subtracting the classical piece, just linearly growing in R. So the way this plot looks like, so there is a Z line, which is kind of that's leading order kind of Nambu-Goto approximation corresponding to that square root formula, where all three states are degenerate. Well, so then there is a spin 2 which goes up. Then there is spin 0 which goes down. And while at large R, which at large R, it's actually agrees pretty well with perturbative calculation. So this is kind of, I'm drawing the sketch of the data. Here, let me draw for you the sketch of the theory. So theory, roughly speaking, it looks like that. So it agrees better than naive expansion, but still it doesn't agree that well. And actually somehow still somewhat miraculously, and that's, we'll see, there is really some miracle goes on here, it looks like. So somewhat miraculously, the actual data still agrees at short distances. It still agrees with the kind of square root formula much better than the perturbative calculation.
But you cannot go to smaller, right?
Yeah, right. So, but in this technique, I know. So I know where my perturbation theory breaks down, because you see what happens is that there is this formula, well, schematically, which I erased. So the perturbative part of the calculation was expanding in momentum p, and momentum p. So the way one does the calculation, one calculates this phase shift, then one solves this equation, and from this equation determines p. And when the phase shift grows, that the p which one determines from this equation is actually it's smaller than the naive one to pi n over r, which physically corresponds to the fact that excited string, its length actually it's longer than the size of the circle. So growing phase shift kind of it helps to improve this perturbation theory. It's related to kind of what we already discussed, like to this some sense UV-IR mixing mentioned by Nati, right? Because this theory is gravitational. So high energy perturbations, they correspond to long strings. And that's kind of what happens. So the theory in some sense improves its own high energy behavior. But anyway, so we know where we stop trusting our expansion. That's where this momentum becomes large in string units. So we have a control. But in any case, it's still experimental fact that kind of the data somehow much closer to the 3-level answer than this calculation. But the really interesting thing is that the pseudo, so that was s equal 2, that was s equals 0, and they still agree pretty well. So this discrepancy is not dramatic. But the pseudo-scalar state, which theoretically was expected to agree with the scalar disorder, well, it falls roughly like this. It's kind of, it strongly disagrees, and also it's the corresponding energy, excess energy, is roughly independent of R. So, well, first of all, kind of the fact that we have controllable calculation now indicates that, well, shows that this disagreement, we cannot blame it on just the bad convergence of perturbative expansion. There's really the gap between these states and those states is much larger.
It happened only d equal to 4.
Yeah, that's a d equal 4. D equal 3. Yeah, actually, in d equal 3, there are essentially for all states, there is quite good agreement with just Bogota. Well, there are some splittings. Yeah, actually, okay, maybe I should say that in D equals 3, let me, before going to D equals 4, because I already said it before, but in D equals 3, so there is no universal particle solution, and at the leading order, one gets prediction that there is a degeneracy between states at the same level, and that's the consequence of integrability. What one finds at D equals 3, one finds that the agreement is pretty good up to, even with leading order answer, down to quite small values of R, but there is definitely splittings between different states. So that shows that integrability is broken. And actually, from these splittings, one can extract, so the first non-universal correction, this alpha R squared term in D equals 3, one can extract this correction and can determine the value of the correction to this spaceship. So from D equals 3 data, we know that even though in principle theory could have been integrable, it's not. So in D equals 4, theory couldn't have been integrable, but also there is this non-trivial structure here. And what this state shows, the fact that this mass gap, energy gap is independent of R, it really, the way it looks like, it's as if we just added extra massive particle. So kind of that picture like that, it's a kind of hallmark of presence of a resonance in the scattering of the massless bosons. And actually there is kind of another pseudoscalar, first excited pseudoscalar state which goes somewhere here. And so basically what one expects, and these values of R, well, they're only now being measured, but actually there is better lattice data. But one expects to find a picture like this, when you have a massive resonance and there is avoided level crossing, which looks like that. So what this data indicates that it shows the presence of the massive excitation on a string, and the fact that it's pseudoscalar, it's exactly, I think Nikita was suggesting in the first lecture. Yeah, it's a twist mode of a string. It's not a radial excitation of a string, but rather like a twist excitation. And furthermore, so now one can do the following. One can just do an effective field theory. One can add this part. So we had action which was non-Bogota plus in principle higher the corrections. But now we can add this new particle. Which is an induced metric. And let me call it A. It's a pseudoscalar. And the first operator, which in derivative expansion, the first operator which couples that particle, there is some mass. And so the first operator which couples this particle to goldstones, first non-trivial pseudoscalar operator which one can write is A K tilde, where this is extrinsic curvature, and tilde stands it's kind of pseudoscalar combinations with epsilon contractions. And the reason I call this guy A, it's because well, it's natural because of this coupling. It's kind of natural to call this particle something like an axion, because actually this term, this operator which appears here, this is quite interesting operator, because it's a topological density. What it does, it was, I think, first in the context of strings was discussed by Polakov. What it does, it calculates when you have a two-dimensional surface in four-dimensional target space, then you can calculate its generic configuration. It self-intersects over an integer set of points, and if you calculate those points with signs, which are controlled by orientation of a surface, that's an invariant of the embedding. And so this particle, it happens to be the case, it's a leading operator which it couples to, it's kind of with this topological density. So it's a little bit like an axion coupled to FF2. This is some topological invariant of
And you want to argue that you can have it only in D equal to 4 without in D equal to 3?
This particular term, right? This topological invariant, presence of this topological invariant, that's special to D equal to 4. Yeah, well, indeed, yeah, right.
What would be the simplest term in D equals 3?
Huh?
What would be?
Well, in D equals 3, well, first of all, well, in higher dimensions, I'll talk a bit
Higher
more.
dimensions, I can see, but in
in-
equals 3, there's nothing.
Right, in d equals 3, one, there, well, I guess, well, pseudoscalar for long string there is no such, because there is no such a thing, right? Because this is, so here we're talking like this is O d minus 2 and pseudoscalar. So in high dimensions, really in the general number of dimensions, one has scalar, symmetric tensor, and antisymmetric tensor. So when it goes to high dimensions, the natural generalization of this guy would be the object in antisymmetric representation of OD minus 2. But
Well, with one transverse dimension.
right, and one transverse dimension, there is nothing left. Yes. Okay, and so from this lattice data, one can determine there is a parameter here, and one can.
So, Sergei, you sometimes describe this as kind of reasonable also in front of your plaquette deformations of the string. In lattice case.
Right, yeah, so in lattice language, it's very natural, yeah, so the operator which produces this guy is that you have long string and then you kind of insert plaquette in the transverse plane, and that can only be done in 4 dimensions or in terms of writing these operators in the continuum. It corresponds if I have a Wilson line which goes in z direction, that corresponds to inserting the plaquette, which is fxy corresponding. So one can insert f z, zx, f zy, which corresponds to attaching plaquette like that, and that corresponds to adding a Goldstone excitation. That's xi modes, but then another natural operator is this one. So yeah, really, I think well we call it axial, but it's properly it's really a gluon. It's just gluon, but with kind of this specific polarization with respect to the long string. So a posteriori, it's very non-surprising to find this degree of freedom. But initially, it was somewhat surprising, and I think many people expect to find at least something like a scalar mode, something like a Liouville field. And there is no sign of scalar excitation, neither in 3 dimensions. Yeah, like breathing mode, but well, this one is also breathing, but with a twist, but radially symmetric, right? But there is no sign of a mode like that. I will comment on that later. Furthermore, from this data, so basically in terms of scattering, the way it's interpreted, I can see the scattering of 2 Goldstone modes, and so this guy in the kind of appears as a resonance in S channel, and that's how I see it in this sector. But also it contributes to scattering in T channel, and that what affects that gives additional contribution to splitting between S equals 0 and S equals 2 modes. So and then I can that allows me from the splitting that allows me to extract the value of this coefficient Q, with this coupling constant, from lattice data, and well, in proper units, this Q is something like 0.38, and this number will be important. And it's determined with the precision, like for the 5% with the current lattice data. And the mass in physical units, the mass of this guy. So yeah, kind of to give you an idea, the mass. There's nothing surprising about the mass. It's kind of in physical units, it's something like 750 MeV. So it's like it's 1.7 in string units, something like that. So it's order 1. It's not a particularly light particle, order 1 in string units, and this coupling, but it's relatively narrow. So the width of this resonance is like 20% or something. So it's not super narrow, but also it is relatively narrow. Okay, so that's kind of that was the end of the summary of experimental data. So kind of in D equals 3, one doesn't see any extra massive modes in current data, but actually up to pretty high energies in string units. One sees splittings, which are not huge, but one sees that series is non-integrable. And in D equals 4, one again sees single additional mode, which has natural kind of gauge theory interpretation and has this value of couplings. Now, as I'll try to argue, well, I will try to explain. Actually, there are two somewhat surprising pieces of numerology associated with this value count. And so, kind of, that's the end of the experimental summary. So, if there are questions from that, it was fun.
How good is it? Does the data match with the theory without adding anything?
Without adding it? Oh.
Yeah. So in D equals to 3, we don't have anything, no extra word, right?
Yeah. So there it matches pretty well, but also, well, one clearly sees that one can extract this parameter also with also pretty good precision. So well, there is no like, well, it's kind of, it agrees at some R's and it starts disagreeing. But and I should say, well, kind of one can also kind of put here. I was doing it coming from low energies, but one can also put this whole logic differently, right? And that's what lattice people do, because at the end of the day, doing this mass of this particle is kind of order 1 in string units. So doing effective field theory expansion is not terribly good idea in such a situation. But what one can do, one can turn these equations, which we use to calculate final volume spectrum, in the opposite direction, and just experimentally from those equations extract the S matrix. And again, that's only possible up to the point when non-elasticities become important, when you have multi-particle production. But before that, one can use these equations, and then kind of what one sees in D equal 4, one just sees that there is a kind of nice resonance in the pseudoscalar channel in the S matrix, and can determine. So really, instead of talking about this coefficient, one may just talk about the mass and the width of that resonance. And in D equals 3, one finds that the phase shift behaves like there is S and like to the IS, and then there is S cube correction with some coefficient, and that coefficient can be extracted from data, and it takes some like reasonable value. So because of doing some kind of counting of pi's and loops, one has estimate for what this coefficient should be, or order of magnitude, and it takes reasonable values. But it is definitely non-zero. So
it's an expansion in small s.
Huh?
It's the expansion in small s.
Yeah, that's yeah. But in principle, one can also kind of try to extract this function to large s. Yeah, this is kind of that was expansion in small s. But ultimately, one runs into the problem that in large s, one sees that there is particle production becomes important, and one needs to find better way to relate S matrix to find volume spectrum, because that equation is not adequate. So yeah, there is some. We also did some estimates for elasticity, but let me find it.
What if you have curvature in high powers in this plaquette picture when you sort of? What if you have curvature in high powers like?
You mean here?
Yeah.
But the expectation is, well, I'm kind of running ahead of myself, but yeah. So from I said that one expects that it should be possible to relate what we see on the world sheet. Kind of there should be some relation to asymptotically free kind of picture of underlying gauge theory, right? And from the picture is, yeah, so what we are studying, one may think about this way. So long string is essentially, you might think about it, some interior of some heavy quark meson, right? You have two heavy quarks, you stretch them very far apart. And then at high energies, well, what are the excitations which we find inside of all hadrons? What is the partons, right? And this is pure glue. So in pure glue, we expect to find gluons. It would be actually surprising to find something else. And so inserting here higher powers of F, it just that would correspond to creating multi-particle states or multi-gluon states here.
So is it multi-particle, or you might have high resonances?
Well, this high resonance, like for perturbative QCD viewpoint, it would be surprising, right? It would be having some kind of bound states of gluons. Well, I don't think we expect to find something like that. And in the data, we don't see any high resonances. Right.
Now, you don't see any narrow. I mean,
yeah, it
there's
depends.
no sharp.
Right. Yeah. In principle, there could have been some like additional broad resonances, but there is no sign of. This one is relatively narrow. Like there is no sign of anything like that in the data. Right. Yeah. In principle, of course, there could be some features, trivial features of scattering of these guys. Now, okay. So, are there any more questions about kind of this experimental summary? So, yeah, now to explain that there is some interesting numerology associated with this value, we need to do a little bit theory again. Well, it's kind of it's related to these two questions which I wrote here, especially to the first one. So one may think, okay, what are the options? Is it possible to find integrable confining theorems? And from the point of view of the worldsheet perspective, what that means, so we said, like, now I'm talking about D equal 4. We said that if one makes an assumption there is no additional massless particles on the worldsheet, there is universal one particle production at one loop, and there is nothing can be done about that, apart from adding additional massless particles on the worldsheet. So as usual, when there is anomaly, the way to cancel anomaly, you need to add extra massless stuff. So it's natural to ask the question, okay, let me start with number God. If I want to get integrable theory, I will need to add some extra additional massless particle and to cancel that anomaly. So what are the options? Well, the simplest option one may think about would be the following. Let's add just a single scalar particle. It should be massless, and let's write that the leading order coupling would be this one, and then one can arrange that the exchange kind of there was a one loop scattering of Goldstone bosons, which was leading rise to well here to annihilations, but with large number of legs leading rise to particle production. So one may ask, okay, whether it's possible to arrange the coupling of this particle in such a way that exchange of this particle exactly cancels this particle production. And the answer is yes. And to achieve this, this coupling should take value square root of 25 minus d over 48 pi. It can be done in any number of dimensions. And of course, what I'm telling you should be very well familiar. It's just a very convoluted way to kind of describe something very simple. That's the way to, kind of from this viewpoint of scattering on the long string, that's the way to rediscover linear dilaton theory. So that's exactly the linear dilaton background, and that coupling is what one needs for linear dilaton to be with the conformal description to get the correct central charge.
Yeah, so I made it a critical string.
Yeah? Right, so that's kind of the standard path to non-critical strings. But that's not what we have here, because we don't have...
No, it's critical in the sense that the central charge...
Right, yeah, exactly, yeah. So this central, yes, the central charge is 26 now, right? So yeah, that's kind of, in the Polakov description, one can recover the same value of Q by doing the central charge calculation. Now the observation is the following. So, okay, that's not what we have. We don't have a scalar, but we have a pseudoscalar. Well, it turns out that from the point of view of asking the question in 4 dimensions now, well, that's only works in 4 dimensions because this operator can be written only in 4 dimensions. So from the point of view of asking the question that I want to cancel particle production, one can try now set this mass to 0 and add a particle like this with this value of coupling. And it works exactly the same way. At the perturbative order, well, and I should say, of course, in linear dilaton case, we know that this theory exists because that cancellation of particle production was at one loop. But we know that this theory exists at all loop order independently. But by arguments similar to how I described for you last time, by these inductive arguments, we also here we have inductive proof. But probably here it's not needed. It's really very overkill. But we have inductive proof that theory can be constructed to all orders in derivative expansion. And the theory actually it's the same S matrix. So it's e to the is ls squared over 4, where all particles scatter with the same phase shift with 3 flavors. But so it looks like, well, actually, it looks like quantization of d equal 5 string. It breaks d equal 5 Poincare invariance, but leaves d equal 4 Poincare invariance. So that's kind of linear dilaton theory. So it turns out that also for pseudoscalar coupling, it works exactly in the same way. So instead of that coupling to Euler density, one can use pseudoscalar coupling to this other topological density. And from the point of view of this question about integrability, 2 situations look identical. So you can find the value of this thing, which cancels particle production, which is given by the same formula.
So it will change the spectrum.
Huh?
It will change the spectrum that you wrote before dramatically, because it will change the d minus 2 over 12 to 2.
Yeah, because if this particle is massless, right?
With the,
No, it will.
with the linear dilaton. Now it's a critical string, so the spectrum will be precisely what you wrote before.
Yeah, it will
but
be.
instead of the d minus 2.
No, I'm not saying it will change. It's a different theory, of course. So here I'm exploring the options, kind of what can be added. I need to add some extra massless stuff. I'm exploring the options, what can be added to reconstruct integrability. Kind of that's the question I'm asking. And kind of that was an illustration that that's not a stupid question to ask. If I were not smart enough to, like if Polakov were not smart enough to come up with his formalism, that would be alternative way to discover the same theory. So, but then what happens is that also following the same logic, one discovers yet another theory, namely theory with this pseudoscalar, and the argument goes absolutely the same. So one first finds this at one loop. It turns out one can use this coupling to cancel particle production. One can construct inductively theory at all of the loop expansion. Well, now that's.
Just to make sure that I understand, you say that the linear dilaton thing is the wrong suggestion, this is the right thing?
Essentially, yes, right. That's what I'm saying, yeah. And the value, so we have a prediction for value of the thing for canceling particle production, it should be equal to square root of 7 over 16 pi, the number, which happens to be 0.037.176. So within error bars, which are few percent, it agrees with the value which were extracted from for this coupling Q for axion on the QCD string. The difference is that axion it's massive, so the mass is there. So the theory is not integrable, but somehow the value of the coupling happens to be the same, which can be interpreted different interpretation of that. One interpretation that, well, like in QCD, whatever you do work at the level of 5%. So all models work. So that's numerology. Forget about this. Another interpretation. Initially, we thought, okay, maybe actually initially we did this for SU3 and SU5 data. We thought, okay, maybe theory really wants to become integrable at high n. That would require for the axion mass to go to 0 at high n. So we asked our.
What n are you talking about? There were many n's on your
NC. I'm talking about NC. So initially that fit was, we looked at NC equals 3 and 5.
The excitation on the end that you wrote before.
No, here all the story was for 2 to 2. All this extracted from 2 to 2 scattering. From.
But might it be that
if you plug d equal to 3,
Huh?
then for d equal to 3, the linear dilaton is very similar, but you know there is no such effect, right?
Well, actually, we'll get back momentarily to d equal to 3. There is uniform way to say what happens both at d equals 3 and d equals 4. Well, so yeah, but just okay. Initially we thought, okay, maybe like the miracle happens, and when I do lattice calculation large and c, that this mass will go to 0, and somehow theory wants to become integrable at high energies. Well, that's not the case. So we ask our lattice friends. They did the calculation. The mass goes changes by 10%. It stays constant. Then the only interpretation which remains for that not to be numerology is that, well, somehow theory wants to become approximately integrable at high energy. So that's how theory unitarizes, by canceling the particle production. So there is transient violation of integrability at scales of order lambda QCD, but as one goes to high energies, in some sense it approaches again integrable asymptotics, which kind of would match this intuition coming that there is a memory about asymptotic freedom.
And
Yeah.
the equation for the energy that we wrote before, when the excitation number is very large, then
So I'm here studying just n that n is n tilde equal to 1. I'm studying scattering of two particle states. Well, one can look at other states, like you can see for other levels, one sees the presence of the same particle. That's kind of cross-check.
So for this thing,
Sorry. You're mixing history with discussion.
Right.
It's always confusing to people who don't know the history. So NC35 was...
But that was initial data which we looked at.
Now it's gone much higher.
Now they essentially Mike Tepper and Andreas and Rose extrapolated to NC to infinity, and they see that this guy is present and the mass goes to constant. So that's one story. But I think the question is about other levels.
Yes, so my question is, might it be that this accident is not accident because when n and n tilde are very large, instead of 1, the two theories somehow coincide, so that m squared is order 1?
Well, but there is still the fact that the mass is not zero. The theory is different. So
It's different.
Right.
Maybe it's different only for low excitation numbers.
well, or for
And it's becoming
no, but also
better and better, at least at the level, the spectrum is roughly.
no, but that's essentially what I'm suggesting, right? So that's that's the only
That's what
interpretation.
it means to go to high energy.
Right. The only sane interpretation of that, which is not just to say that it's sheer coincidence, is yes, that if one goes, well, I just prefer to phrase it not in terms of excitation energies, but in terms of the phase shifts. That one looks at the S matrix, that in some sense, kind of, it's a little bit tricky, but we can discuss. But that in some sense, in high energy theory wants to reach this these integrable asymptotics. So okay, that's one piece of numerology. Let me briefly mention for you. There is another piece of numerology which is probably not completely unrelated to what happens here, which is the following. So recently, Pedro Vera with friends, what they did, they applied S-matrix bootstrap to this problem. So we have a sharp way to ask the question what QCD string is. So that means to look for S matrices on the long string, and there is now people after success of the conformal bootstrap, people trying to apply similar techniques to S matrix bootstrap. And the way it works, essentially, they obtain in parameters. So they so if one looks as start as Nambu-Gotter plus higher order operators. So they in the kind of space of these Wilson coefficients, they obtain the constraints on the values of this coefficient, and kind of the way the typical.
So what alpha?
Well, alpha 1, alpha 2, there are actually in 4 dimensions there are 2 different operators this order with different contraction, like with r squared and k. No, they're not. No, because for bootstrap purposes, that state is not there because it's not stable asymptotic state. So that it's just a resonance. So they study a series of 2 massless states, and they impose. Now they impose essentially unitarity constraint in the 2-to-2 scattering channel. And as usual in the bootstrap study, there is some kind of some excluded region, there is some allowed region, and there is a boundary between them. And
Which is the excluded, by the way?
excluded is, I think, that's a good question. What I'm drawing here. No, because there is integrable theory. I don't remember on this spot, but I think I know. No, I think that should be allowed region. Right, because I remember in d equals 3, the value of that coefficient it cannot get too negative, and like the value which we found here. It is positive, and the right order magnitude is the same as the boundary.
Usually the convex region is the allowed one.
Usually what?
The convex region is the allowed one, right? So you have the cusp.
For me, it's equally confusing what is convex and what is
No, but
concave.
the one you mean.
Yeah, I think so. Yeah. So, and what they found is the following. So there is boundary of allowed region. And it kind of has, and there are, it's natural to look what happens at the boundaries of this region. What are the series which one finds at the boundaries of this region?
Which boundary is smooth? There are no cusps.
Well, it's smooth. There are no cusps here, but there are kind of 2 parts of the boundary, and So on these two parts, what one finds, I should say that the series which lie at these boundaries in this case, they're not physical series because this S-matrix bootstrap, well, it only knows about 2 to 2 scattering, and the constraint of nonlinearized Poincare symmetry, it relates amplitudes with different number of particles. Well, in particular, the series which they find on these boundaries are naturally without particle production, just by the way these constraints are organized. So they cannot be
the constraints are unitarity.
Right, the
Which
constraints.
is obviously the boundary with.
Right, yes. So really, kind of, in its present form, this S-matrix bootstrap is not good enough to really find physical series, but maybe for that one needs to include multi-particle constraints. But maybe one day, well, but anyway, something very interesting happens still. So what they find is the following. So kind of there are two regions on this boundary, and on one region, if one looks at the theory kind of at the boundary, then they find that there is a light, and that for sure I'm not being accurate here on which one. But on one part, they find that there is a like relatively narrow scalar resonance, and that's kind of what one expects in the kind of, that's roughly speaking, kind of holographic series or standard non-critical series, right? So that's where there is Liouville-like mode present on the string. And on the other side of the boundary, they find that instead there is a relatively narrow pseudoscalar resonance. And moreover, again, within the error bars of their numerical simulations, there are because for this resonance, they don't write Lagrangians. What they determine the position of the resonance. They determine width to mass ratio, but which is the same, which is related to this parameter. So again, within the error bars of what they're doing, it corresponds to the same value of Q, which is again at the level of few percent.
You said when you reported the lattice data, you said that m over m was 20%.
Yes, right.
And that's equivalent to that value of Q? I mean, what sense?
Yeah, so, well, because this operator for massive A, it gives rise to decay. A can decay to Goldstone bosons. And that corresponds to this 20%, that's what I get for this value of Q.
And measured value of Q
And
in lattice gauge theory agrees with that?
Yeah, so my measured value for lattice agrees with that. That's the first piece of numerology. And the second piece of numerology, the gamma to m ratio extracted from bootstrap also agrees.
The boundary agrees.
Yeah, the boundary, right.
All points in the boundary? There
Uh,
are many points in it. It's a big boundary.
Right. Somehow, let me try to remember. Well, there is a, because there is a, they have, well, somehow they have a point, but there, different points, they correspond to these parameters alpha, but then there is, I think the kind of choice of the point of the boundary, I think that corresponds to picking value of m.
You said that all of them have the same gamma over m? All the boundary theory?
That's, yeah, let me. Yeah, if I understand what they're saying, yes, their answer would be yes. They draw different points here, and these different points, they associate with different, like, they say, oh, this is SU3, this is SU5, and as I understand, that corresponds to, because the mass somewhat changes from SU3, SU3 to SU5. So gamma, but this ratio, yeah, so this ratio stays the same. Right? Yes, that's, I should double check, but that's the only interpretation. I can see what happens. Well, maybe kind of sufficiently because there is obviously some transient regime there when one goes like from anti-scalar to anti-scalar. but the values of the masses which correspond to kind of those masses which one has here, they're already sufficiently far away there. And in that asymptotics, that value which they extract, it again agrees with the same. Which kind of, I think again, the interpretation of that would be really, so that's how this theory want to unitarize. So that's.
And so we make, but this is a numerical calculation.
Yes.
And they get a Q from this.
Well, they get this ratio,
They get this ratio,
which can be translated.
constant.
Yeah.
And how does it compare with 0.38?
Yeah, that's the same. Yes, it agrees with the narrow bars with the 0.3. So that's kind of the triple numerology.
Where are the error bars? Who's calculating?
Well, the error bars here, as I said, they are like roughly the level of like 5-10% from lattice. From lattice. There, I never I asked this question several times to these guys and never managed to get the answer about exactly error bar, but they say it really agrees. but presumably that means it's better than this.
But you, I mean, really agrees with something that you have no error bars.
I mean with no. I think what they mean with lattice, right?
But you has to agree with set square root 765.
Well, it's.
What kind of?
Well, that's not exactly, as I said, that's not exactly correct theory, because that theory which they have doesn't have full Poincare invariance. So they find, but
Not sure, but well, they have. The Woodstock only gives constraints, but sometimes it actually ends on the boundary.
yeah,
Yeah, right.
right. No, yeah, actually, yeah, I don't know yet how well it agrees with this number. I think they were comparing with the last number extracted from lattice. It agrees from there. So yeah, basically, well, that's kind of the current summary. Yeah, so coming back to what Kobe was asking, right, about d equals 3. Well, actually, the picture looks, both at d equals 3 and d equals 4, it looks in some sense the same, right? So at d equals 3, we saw at d equals 3, it's possible to have integrable theory with e to the ISS matrix just of a single Goldstone boson, and kind of the theory which one finds on the worldsheet. It has the only degree of freedom, and it's not exactly that theory, but it's natural to think about this, and maybe it is deformation of that theory. So at d equals 4, we can't have that theory, but we may have theory plus this axiom with the same S matrix, and that's what one finds in d equals 4. So in both cases, one finds meta content of a possible integrable model. In both cases, theory is not integrable. But kind of there are some non-trivial indications that.
What did the Woodstock people find for d equals 3?
No, for d equals 3, they just find the some bounds on this coefficient, but they
don't find this.
yeah, they don't. Yeah, right. Well, again, because that theory is there, so e to the s.
Right, but they're doing it differently. So
Yeah, it's a different way. Yeah, right. It's somewhere far away. Yeah, they don't find anything particular there. Yeah. Well, so that's the current situation, and well, I think kind of to continue this, well, that's numerology again. To take it seriously, it suggests that it should be possible. Like the hope would be that if one understands well enough these integrable models, then one may try to develop some kind of perturbative expansion around that integral models which would describe the actual QCD string. It's not clear, well, this interesting question, whether these integrable models on themselves, whether they really correspond to consistent string theory. Well, I don't know the answer. My gut feeling is that the answer will be no. That somehow there is a reason that the theory is not integrable. That somehow that these models are not exactly like healthy theories, so there is something which prevents from theory being integral. But I don't know the answer. It's just my prejudices. Well, how much time I have?
Well, remember that you're going to...
Okay, maybe I will say one last thing. Yeah, so, but that's not related directly to QCD, but one may wonder whether it's possible kind of there's this pattern which appears at d equals 3, d equals 4. What about d larger than 4? Is it possible to do something like that? And the situation is the following. So generalization would be, as we said, so generalization would be that instead of writing pseudoscalar, really like we had these three channels: scalar, like antisymmetric tensor, and spin 2. So one wants to write something like antisymmetric tensor with respect to OD minus 2, and kind of there is some operator like this, which that's kind of the operator which was written here. So that's in the four-dimensional case, it's just A times epsilon ij. That's how pseudoscalar appears. But in higher dimensions, one would need to write operator like this. I don't know whether, so as far as kind of just particle production at one loop goes, it can be used in the same way to cancel it. But here situation is much more complicated because of the fact that now kind of OD minus 2 group is non-abelian. Actually, if one wants to introduce such a guy with a such that this action should be invariant under the full ISO 1 d minus 1, so there should be non-linearly realized Poincare symmetry. So in 4 dimensions, because it reduces to scale, it's kind of trivial to achieve. But in this case, just to write even kinetic term for this guy, Ag squared, on its own, that kinetic term wouldn't be invariant under non-linearized symmetries. One can go through coset construction with extra matter in this representation, and what one finds that there are non-trivial interactions of this guy with x's, additional non-trivial interactions with x's, such that even at the leading order in derivative expansion. So for axion, at the leading order in derivative expansion, this integrable theory just has Nambu-Gote action of x's and a. So here, at the leading order in derivative expansion, it cannot be that simple. And actually, the bottom line is the following: we don't know whether the theory exists, but if it exists, then kind of it requires also to start adding to obtain integrability. So it requires to start adding terms like this, trilinear couplings, and then one can do the following exercise, because we even don't know what the S matrix for the theory to expect. But let's say we expect the same as in other cases. So it's again bunch of free scalars and this antisymmetric guy, and everything with just diagonal e to the s. And let's ask the question whether it's possible to find Poincare invariant theory with this S matrix. As a first step, one needs to start. One starts with this Lagrangian, and the zeros on the step. One just needs to find an action of A's alone, such that kind of in the leading order in a less expansion, such that it would have trivial S matrix. And it turns out that it's possible to achieve, and there is a unique Lagrangian which achieves that. Namely, kind of similar how one starts with kind of d phi theory, d phi squared, and then m squared phi squared, and lambda phi to the 4, and then imposing integrability, one can reconstruct sine Gordon potential, right? So here it's somewhat peculiar situation. One starts with a theory like that, antisymmetric tensor, adds operator like that. So there is epsilon symbol here. And this operator has peculiar property that it vanishes on shell, but cannot be removed by field redefinition. It's a peculiarity which is only present in 2 dimensions, essentially. And one may ask, what we need to find an infinite series of operators which complete this and still have the following properties. So one has some non-trivial theory where one cannot remove things by field redefinition, but all amplitudes vanish on shell. And the result that can be done in a unique way, and what one recovers WZW model. So the statement, if the theory exists, and I'm not sure how to think about it from the point of view WZW, but if the theory exists,
WZW for exponential of A?
Huh?
It's for exponential of A?
Well, yeah, exactly. So A should be thought of as being in the adjoint of the OD minus 2, and one recovers. So the statement is, if this family of series exists, we don't know whether it really exists or not, but if it exists, then at high dimensions, what one needs to add? One needs to add OD minus 2 WZW model.
Because the motivation you have from asymptotic field was looking
Yeah, there is no motivation. Because we don't know confining series in high dimensions, but linear dilaton exists in any number of dimensions, and again, from the viewpoint of integrability, the story looks similar. So it's natural to ask other series like that in high dimensions, and we don't know at the moment at high dimensions. Apart from the fact that if they are, then it should be kind of Goldstones plus WZW on the long string. And of course, the challenge is how to, because the difference with linear dilaton, that linear dilaton can be rewritten in Polakov formalism. But here we have coupling to extrinsic curvature, so we don't have, so from the point of view of integrability, the series question, the series looks like this. Axion and scalar series, they look exactly the same. But the difference is that for one of them, we know how to rewrite it in the Polakov language, and we have a CFT formulation. For the other, we don't. And that's kind of the challenge. Yeah, let me pause here.
Are there any other questions, Sergei? Not to thank you for this wonderful